I'll be talking about the beginning of the universe. I also want to emphasize a theme, which is that our understanding of the universe has really become shockingly successful in understanding many features of the universe, and we're even able to predict many features that the universe has shown us to be real. On the other hand, we're also shockingly ignorant about some of the basic features of the universe, like what all the stuff that it's made out of is. And I'll try to make it clear how that all works. So I want to describe this theory called inflation. But I want to begin by first saying a few words about the conventional Big Bang theory that existed before inflation was invented. The Big Bang theory essentially is the theory that the universe as we know it began some 13 to 15 billion years ago. And we now even know this number quite accurately, we think. According to the latest data, the age of the universe is 13.7 plus or minus just 0.2 uncertainty billion years. I added this phrase, as we know it, as an intentional hedge. Cosmologists know that we need to hedge. The era that we think we can describe, we're quite sure began about 13 to 15 billion years ago. But we really don't know what happened before what we normally call time zero. There's a lot of uncertainty there, and there is certainly room for a possibility of a very significant prehistory. And there are theoretical discussions of such things, and they might also be correct. The initial state of the universe, and by initial I now mean 13 to 15 billion years ago, was the state of a hot, dense, uniform soup of particles. And it is important, it's been emphasized by, I think, almost every speaker who's spoken so far, that this initial soup of particles filled the entire space. It was not a small egg in the midst of an otherwise empty space, as is often pictured in cartoons. The traditional Big Bang theory is very successful in many ways. It describes how the early universe expanded and cooled. It also describes how the light chemical elements formed. And it gives us a description of how the universe congealed to form galaxies, stars, clusters of galaxies, and so on. Certainly this later point is still a work in progress, but we certainly do think we understand the basics of how those processes happened. Nonetheless, there are a number of features which are not described, not even attempted to be described by the conventional Big Bang theory. And I'd like to highlight two of those. One of them is the question of what caused the expansion. Now, everyone would naturally think the bang of the Big Bang, naturally. It's called the Big Bang theory, but in spite of that name, it never really was a theory of a Big Bang. From the very beginning, as far as its scientific formulation, the Big Bang theory was really just, excuse me, the description of the aftermath of a bang. The theory says nothing whatever about what banged, why it banged, or what happened before it banged. So inflation actually is an attempt to try to answer some of those questions. Another important question is the question of where the matter in the universe came from. In the conventional Big Bang theory, without inflation, all of the matter was assumed to be present from the very beginning. For every particle that exists in the universe today, it was assumed that there was at least a precursor particle that existed from the very beginning, with no explanation of where all that matter came from. Inflation actually offers a possible explanation for the origin of essentially all of the matter in the universe. So the key to trying to answer those questions, as I indicated, is to introduce the idea of inflation, and this actually repeats the transparency shown by Max Tegmark. The idea is that from the beginning, or at least what we call time zero, whether or not something happened before it, we introduce a tiny fraction of a second of evolution followed by the onset of inflation. Inflation lasts perhaps 10 to the minus 35, 10 to the minus 32 seconds, something in that range. Then the universe continues to evolve by mechanisms that we think we already understood for about 380,000 years before the release of the cosmic background radiation. And then we are observing that cosmic background radiation today in a universe which we believe is about 13.7 billion years old. So what is inflation? In a nutshell, I want to describe it now in a few transparencies. The key idea behind inflation comes from particle physics. The idea is that modern particle theories actually predict that at very high energies, we expect there to exist forms of matter which literally turn gravity on its head and cause gravity to become repulsive, creating a genuine gravitational repulsion. So inflation is the proposal that at least a small patch of this repulsive gravity material existed in the very early universe. And there are various theories about how that could have come about. That's still very speculative. One doesn't need a very big patch of this material. The initial patch that began inflation could have been smaller than 1 billion times smaller than the size of a single proton, which is really amazing. These numbers basically come out of the numbers associated with grand unified theories in particle physics. Once this gravitational repulsion started, it would drive the universe into a period of exponential expansion. And using typical numbers, again coming from grand unified theories, the doubling time for this exponential expansion would be about 10 to the minus 37 seconds, a decimal point, 36 zeros, and a 1, that many seconds. And what I mean is during that period of time, the universe would double in size. During the next interval of the same duration, the universe would double again and then redouble and redouble. That's what exponential means. We need about 100 of these doublings to create a universe starting from something more than 1 billion times smaller than a single proton. An important and very strange feature of the exponential expansion driven by this repulsive gravity is that while it's taking place, the density of matter does not go down. Now, if you had any normal kind of gas and you expanded it, the density goes down. That's what we're accustomed to. But from our understanding of elementary particle physics, we believe that this is not the case for the kind of expansion driven by this repulsive gravity. The density of matter actually remains constant. Now, this sounds like it would violate the idea of conservation of matter or conservation of energy. It doesn't for a very special reason related to the fact that it's being driven by gravity. So gravity is playing a crucial role here, and therefore the energy of gravity is crucial to understanding the energy balance. It turns out, and it's a fact which in principle is well known for a long time, but was not widely heralded until inflation came along. The idea is that the energy of a gravitational field is actually negative. So what happens during inflation is that as the tremendous exponential expansion is going on with a constant density of matter, more and more positive energy is appearing in the form of this tremendously increasing amount of matter. But at the same time, more and more negative energy is appearing in the form of the gravitational field, which is filling this region. So the total energy, including the positive contribution from the matter and the negative contribution from the gravity, is at all times very small and could in fact be exactly zero. There could be a perfect cancellation between the positive energy of matter and the negative energy of gravity. So the total energy is conserved, very small, and may be exactly equal to zero. Now, we need to understand how inflation ends, because the universe today, although it now appears to be undergoing a very slow form of inflation, is certainly not inflating at the timescales that we were talking about in describing the early universe. But inflation has a very natural end, because this repulsive gravity material that's predicted by particle physics is itself unstable. Unstable in the same sense that radioactive elements are unstable. So it decays, much like a radioactive material, and when it does, it produces products of that decay, which are just ordinary particles, which form a hot, dense soup of particles, which we often call the primordial soup. Now, this period of inflation could have been very short. It could be as short as 10 to the minus 35 seconds. There's certain uncertainty in the exponent there. At the end, the region of space that's destined to become our presently observed universe is very modestly sized. I have written on the screen a marble, something that you could hold in your hands, although it would be much more massive than anything you could hold in your hands. This primordial soup that I mentioned, the byproducts of the decay of the repulsive gravity material, ends up having exactly the properties that had been assumed for the conventional Big Bang theory. So one of the beauties of the inflationary theory is that it did not require anybody to give up anything about what we previously thought about cosmology. Inflation just very naturally sets up what had been previously assumed as the initial conditions for the conventional Big Bang theory.